Can I add some?
This is our class number 7. Today is Thursday, April 25th. I'm with the Thursday class, which means you get the good presentation. Somebody needs something?
Can I add something?
Yes.
Yeah. Okay. No, I go swimming all year round in the Thames. It's a non-tidal bit, and so far I'm alive. Okay, I'm alive. It's
That's
much
good.
better than it used to be. And then I swallowed a whole lot on Monday, and I'm still fine.
That's a good report.
Yeah. No, it's okay. So well done, the water people, because once upon a time it was just sewage.
Impossible. Yeah.
Yeah, it was impossible.
Right.
So
Right.
well done them.
Right. There are some advantages to capitalism and
Yeah.
even a little bit of advantages to certain government people who actually know what they're doing. Not very
Yeah.
many. All right, let's get started today. I'm still building up the foundation for the heat pump, which probably will come next week. Yeah, Christian.
Yeah. Okay, sorry. Just a question from the lesson last week
Okay, sure.
about Henry's law.
Yes.
The fact that if you have increasing temperature, more gases from the atmosphere would be dissolved in the oceans.
Would be released.
Sorry, with the higher temperature, it would be released, yes. And the lower temperature, the more would be
absorbed.
And that makes good sense. So if it's colder, you would have more CO2 absorbed in the oceans.
Or more air too, just air.
Well, that was my question when we talk about the concentration of CO2 in the atmosphere. As more CO2 goes into the ocean when it gets colder, the same would apply for all the other components.
Yeah. All the gases. All the gases. Yeah.
So is it fair to say that
that's how fish breathe?
Yes, but is that fair to say that in that sense there's no correlation between the relative part of CO2 in the atmosphere when the temperature goes down? I don't know if you understand what I'm saying, but it shouldn't matter what the temperature is and how much CO2 is stored in the ocean when, yes, you absorb more CO2, but you also absorb more nitrogen and oxygen and other components. So the relative part, CO2 as a relative part, or ppm in the atmosphere, shouldn't change because of that.
Right, but I'm pretty sure that the oxygen and nitrogen gets mixed out pretty quickly, pretty early on in the first few meters. And I think the CO2, look, the CO2 goes into shell making. So all of this happens at the surface. Fish use it to breathe. Nitrogen just comes back out and goes out and in all the time. And the CO2 gets, combined with and bound to calcium ions right away.
Okay.
And that gets inhaled by little creatures that are filter feeders, and they use that to make their shells.
Okay.
Right. So if there weren't those creatures, you just have a bunch of calcium carbonate laying around on the surface, and it probably just goes down to the bottom too. Right. Both those, one of the ways it gets heavier, right, when these two atoms combine, or molecules, and then it just sinks. But much of it is ingested by animals that use it for making shells.
Okay. Thank you.
Okay, so all the action happens like in the top 2 meters or so. Okay. All right. Let's go. I've got the following sections to go over. And again, I don't want to rush. I want to show a lot of material, but I don't want to rush. So stop me and make sure you understand what I'm saying or what I'm presenting before I move on, because I just don't want to, I don't want it to just be a blur. Okay. So ask. Also, I try to repeat myself in different ways. So different things come at you in different ways. And so over time, you kind of get it from different angles. I have also a possible bonus section today at the end. We'll see if we have time. All right, we're going to do heat and heat transfer. This is really about heat transfer. So we know that temperature is the speed of molecules. And we know that heat is really the number of molecules going a particular speed. It's really about the mass of molecules going a certain speed. And the types of heat, we're going to break this down. And this is just so you understand the nomenclature, the language. When you hear sensible heat, is really just incremental heat. It means there's no phase change. When your room goes from 21 degrees to 22 degrees, that's just sensible heat. And latent heat involves a phase change, usually for water, evaporation, or freezing. So we can break it down a little bit that conduction is the heat transfer from the heating element of your stove to the top of the pan where you cook. It goes through the metal, and the metal equilibrates. The metal brings the temperature from the speed of the molecules from warm to cold. And so heat flows inside of a substance from warm to cold. That's conduction. And then convection is air currents, rising air that is encouraged to go up because as it expands, it rises more. It wants to expand. So you think about all of the atmosphere at the Earth's surface is under quite a bit of pressure, 1 atmosphere. And as it goes up, it's like, oh, this is great. Well, let's expand even more. So it keeps going up. So that helps it rise. And of course, it cools as it rises. But convection is generally, powered by heat, right? Heat wants to go up. So rising parcels of air, that's convection. And this is sensible heat. And then we have evaporation and freezing, that's latent heat. And then radiative is photons, as we know. So now here's a little chart to get us started. To raise the temperature of 1 gram of water, 1 degree centigrade at sea level requires 4 joules. That's the definition of a joule, I think. Yeah? Somebody? To boil that water from 99 to make that last 1 degree, and that's a phase change. So that's latent heat, requires how many joules?
396.
That's very close for freezing, but it's not for boiling.
Okay.
The boiling number is a different number. So for boiling, it's 2200 joules. So look at that difference. Okay. To raise it 1 degree in general is 4 joules, but that last degree requires 2200 joules. It's a tremendous amount of latent heat, or it's a tremendous amount of energy to go 1 degree, because that last degree frees the molecules and they're now in vapor form. And that's a lot of energy going into the speed of those molecules speed up dramatically from whatever they were before to, hundreds of times or thousands of times, I don't know, faster as they're now in vapor. So that's a lot of energy. Now to lower the temperature, here we go, Corin, 1 degree also requires 4 joules. It's the same up and down. That's sensible heat. It's always incremental. But to freeze it from 1 degree down to 0 requires how many, Corin?
396.
Right.
Hooray.
330. Very close.
Oh, 33. Yeah.
That's right. And these are joules, and I don't know what a joule is. So it takes a lot of energy to change the state from a liquid to a solid, or a solid to a liquid. It goes the other way. It's the same 330 joules either way, right? So about 12% of the reflected energy coming off the surface of the Earth escapes straight to space via the atmospheric window. We know that very well. A small amount of energy goes up via conduction, which is really just molecules bumping into each other. Oxygen and nitrogen, transferring their energy and their speed into the next molecule, which eventually can go up. That's not very much. But then there's convection, which is rising air currents, and that's a lot. So rising air cools as it expands. That's called adiabatic cooling. Adiabatic is kind of a fancy word you might hear, and all it really means is as you go up in altitude. That's all adiabatic really means, because as you go up in altitude, it cools. So it's very associated with the lapse rate, adiabatic. And as the gas expands, it's always going to cool. That's part of what drives the lapse rate. So more energy goes up via convection, much more than conduction. Conduction is just kind of a small part of the chain that's available to molecules as the energy moves up. It's like a wave, right? A lot of these, sometimes the molecules actually move up, and sometimes they just pass energy through them like a wave. But there's another mode, and that's evaporation. So a huge amount of energy goes away from the surface through evaporation. And that's the water cycle. It evaporates energy, those incoming high energy photons, evaporate water, one molecule at a time, transferring the energy into water vapor, which rises and goes into clouds. As the heat comes out of the clouds. Now this is stored energy going up. Then the heat comes out of the clouds at the top as the water condenses, and condensation is the reverse of that same amount of energy. So you get 2,200 joules coming out when it condenses. And that is long wave photons. So as it condenses, it expresses that energy, or that energy, I don't know the right word, comes out of that phase transition as it condenses and turns into long wave photons that escape. And so if you think about it sort of, from the surface where there's water, it will evaporate, rise through convection, condense at the top, and probably there's a little bit of conduction maybe, but then, it escapes. It gets to the emission height that we're familiar with, and they go away off at the speed of light. And that's how you move energy from the surface to space. You could do it through the atmospheric window straight, take the shortcut, but if you've got water around, you're going to do through the phase transitions and the moving the heat up through the air column as water vapor. Okay. And then when there isn't a lake or ocean, and it's done more radiatively in the way that we talked about last week with the long, complicated path and the greenhouse molecules. Remember that last week? So, and that's just because there's no water available to make the phase change. So it's just long wave photons trying to make their way to space. Okay. If you remember this from last week, the oceans cool as a result of evaporations. It's giving up energy. And right above that, about 10 kilometers, that energy comes back out of the water and makes its way to space. So evaporation transfers energy from the ocean to the atmosphere and then to space. Does that make sense? And then whereas the land has to do it the hard way via this random interaction of long wave photons trying to get out through the through the blanket of the greenhouse gas molecules. Now last week, Mark Lawrence said, yeah, but when it comes out at the top doesn't it release less energy? And the answer is, yeah, it does. So on the way up through convection, the water molecules are losing energy. They're spreading out, they're cooling. The air is cooler up there. And by the time it gets out at some, 4,000, 6,000, 8,000 feet, it releases a little bit less energy than went in because it's been releasing all the way. And if it gets up to 10,000 feet, then you're going to get 1,800 joules out of it. But you can see that the total remains the same. We start with 2,200 joules going into the water vapor, and that whole 2,200 joules eventually, through different mechanisms, gets to the top of space and then turns into infrared photons and goes out. Does that make sense? It was a good question last week. I didn't know the answer, so I'm happy to present this collaboration with GPT, showing me that, yeah, it does, but not a lot. Here's 1,800 joules at 10,000 feet. So still a lot of energy, latent energy coming out of water vapor at 10,000 feet. Does that make sense? Everybody with me? All right, so here's the thing I want you, doesn't matter to me if you remember that. I want you to remember this. It takes a lot of energy to melt ice. Melting ice is the opposite of freezing, so it's 330 calories for every gram. Each summer, starting in March, sunlight melts an area the size of the United States that is 2 meters thick. That's how much ice melts over about 4 months. When ice melts in the Arctic all summer long from direct exposure to incoming sunlight, that is not a heat wave. It's not weather. That is the Earth's way of storing energy. Changing from ice to water is storing the 330 joules. It's like a battery. Does everybody see this? That energy is moving across, let's say, Canada or Russia. It gets to the Arctic Ocean. It just comes in from the sun. And all that energy that is cooking the ice, that is melting ice, gets stored in the water, just like a battery. So when the water freezes 6 months later, it releases that energy that is in the water. It's like potential energy. And that energy, when it freezes and gets cold, that energy has to go somewhere. So you think, oh, it's just getting cold. No, it's not getting cold. It's releasing energy into the air column above. It goes up through the low pressure zone in the polar vortex that we're going to discuss in a minute to space via long wave photons at the rate of about 330 per joules per cubic centimeter of water. So it's an energy transfer process that is cyclical. It takes 6 months. Does that make sense?
Yeah. So phrases that are unphrases, and at both times it takes or releases energy.
Right. So there's two ways to melt ice. One is direct solar heating of the Arctic ice, and the other is warm air currents coming in. We're going to see more of that in the next few minutes. Those are the two ways, and both of those store energy. So when you see this diagram over here of summer ice being so low, that is stored energy. This is stored energy waiting for its turn to freeze out and make its way to space. Hi, Imani. We're talking about heat transfer here, and I'm just basically done with this one. So the bottom line is when ice melts, that water is storing energy for the time later. When it freezes, it releases the energy.
So we call that energy storage in buildings thermal mass. So our buildings...
No, because there's a phase change.
Oh, okay.
No. This is latent heat. You don't have latent heat in buildings. You have sensible heat.
Right.
Right? This is latent heat. That's a phase change. It's because there's a huge spike as soon as you go to that last degree. Okay. And that's very different because it's very nonlinear. And sensible heat is essentially linear. Okay. All right. So that's heat transfer. And we're going to use this building block many times as we go forward. Any questions about this? I really want you to get that it's not like a weather event or just melting. It's not melting, it's storage. Okay.
Sorry, David.
Yeah.
Where is it stored?
In the water, because that water was ice.
But the water moves underneath.
No, not really. It's let me just make it clear. There's 2 meters thick of ice. When that turns into water, it doesn't really go very far because there aren't big currents in the Arctic Ocean. There are some that go down and up, but it just doesn't flow away because water's always there. So it just transfers that energy into warmer water in the Arctic basin.
So the water that flows up from the equator,
for example, the Gulf Stream.
The Gulf Stream, that adds to it in the summer as well and stores it.
Negligible, believe me. We'll get to it, but not much. The warm water coming into the Arctic mostly just powers the local weather and is not a big part of the heat pump, as we will learn. And by the way,
thank you.
That's what I thought too. I thought it was all about ocean currents pumping hot water into the Arctic. I was wrong.
Okay.
So it comes in through direct solar radiation because it's very sunny in the Arctic. There's no night for 2 months, 3 months, right? Above the Arctic Circle. So there's a lot of incoming photons and it comes in over through the atmosphere. Okay. All right. So we will move on. But when it freezes, it releases energy. I want everybody just to really burn that in. When water freezes, it releases energy. Okay. And when it evaporates, it releases 2200, it releases even more when it evaporates. These phase changes are very important. All right. Let's go to the next section, and that's temperature gradients. So understanding these 3 gradients helps understand how the Earth moves the heat from the equator to the poles. I'm still building up a big mystery here for everybody that we know that Earth, the Earth has to move heat from the equator to the poles. I'm just putting down all these planks as foundation so we can see it in action probably next week. All right. So the sun's energy arrives in the form of high energy shortwave radiation, photons. About 170 petawatts arrives to Earth at all times. The numbers aren't that important, but I'm going to break it down a bit. About 30% bounces off into space, and that leaves 120 petawatts to hit the Earth and be absorbed, and then has to get out later. Okay. So there are 3 temperature gradients that do that. It's amazing that you don't hear anything about temperature gradients because the people who are experts on climate change, they don't know about temperature gradients. They just know what they hear on the news, and the Guardian tells them. And so we've got 3, the lapse rate, which we've already seen goes vertically up from the surface to space, the overnight gradient, and the meridional temperature gradient, which is abbreviated MT. So if you see MT, especially in Javier's book, meridional temperature gradient. So let's look at the lapse rate. This is going to be very quick. This is very small, short. The lapse rate in the troposphere, this is down here till the tropopause. This is the one we know, varies according to the moisture and the greenhouse gases of the atmosphere. These lapse rates, especially in the troposphere down here, prevent nighttime temperatures from getting too cold at the surface. This is how the Earth really is. with the sun overhead at noon and then trailing off towards sunrise and sunset at the edges. So the second gradient is the overnight gradient. It goes from about 3 p.m. when it's hottest to around 6 a.m. when it's coldest. At nighttime, the atmosphere retains much of the heat, which allows complex life to flourish. That is the greenhouse effect. The greenhouse effect, remember, the largest part of the greenhouse effect by far is water vapor. The greenhouse effect retains heat in the lower atmosphere and delays its escape to space like a sweater, wherever there's a positive lapse rate. So in Jakarta, you can sleep outside overnight because the greenhouse effect from water vapor keeps you warm all night. But in the desert, where it's dry, there are huge temperature extremes because the only greenhouse effect there is a tiny one from carbon dioxide. So you get the idea how small the carbon dioxide greenhouse effect really is. It's the difference. It's what you get in the desert, which is life required for life as we know it, but it isn't much. Make sense? That's why we call it the pilot light. It just keeps your desert from being like Mars when it's dark. You can't live on the Mars or on the moon when it's dark. That's the difference right there. Is the CO2. All right. Now we come to the complicated one, and that's meridional heat transport. We're going to spend the next couple of weeks on this. Okay. So we're going to divide the Earth into 3 zones: the tropics, the temperate, and the polar. And the tropics have different definitions. There are more formal definitions. I'm going to use a loose definition. Right now, I'm going to say that the tropics are 30 degrees north and 30 degrees south of the equator. The temperate zones are from 30 to 60. And then the Arctic is 60 to 90. And that's just to keep the math simple, to be honest. These are arbitrary zones, but we'll get more into how they really are. Tropics, these tropics with the 30 degrees covers half the surface, but absorb 2/3 of the heat coming to Earth. I have to see if I'm recording. Am I recording? Yeah, I'm recording. Good. Okay. Great. Now I'm going to share. Thank goodness. All right. Perfect. There we go. All right. Now we got to go away. Oh boy, I'm in the wrong deck. Sorry. I blew it already. Here we go. There we go. All right. So the tropics are half the surface area, but absorb 2/3 of the heat coming to Earth. This is because outside the tropics, the angle of the sun is spread over a larger distance to get through more ozone and more particulates and so forth. So the heat has to come through more atmosphere up here. And so most of the heat enters in here where it has direct exposure to the sun. Now, just for an accounting trick, if we widen this area to 40 degrees north and south, we have a net energy surplus in this region, the expanded tropics, and a net deficit everywhere else. Again, the Guardian isn't going to tell you this. Heat has to move from the surplus to the deficit. And this is another way to look at it. Up to 40 degrees north and south, there's a surplus of energy. And it just can't possibly radiate straight back out. It's got to move to where it is colder and the heat can escape. So nowhere on Earth is really in balance. Heat is always moving. I mean, the only place on Earth where the heat comes in and then goes straight back out is like right here at the 40-degree line. Everywhere else, it's got to move. Makes sense? All right, so this is the data behind that from Javier's book. The light blue dotted line represents the incoming energy from the sun. Here's the equator in the center right here. And this is This is actually clouds right here, about a little bit north of the equator, that are just more permanent. And then on the left side, annually, the red line shows outgoing long wave radiation, and more of it, that's the left and right, and more of it leaves outside the tropics. But you see this 40-degree line here. See the 40-degree? That is the balance point. So we have a surplus inside of 40 degrees, and we have a net deficit outside 40 degrees. And that's the blue shaded areas. And if you look, you'll see that this blue shaded area is a little bit bigger. So more heat goes poleward to the North Pole and a little bit less. And that's in the ratio of 6 to 5. 6 petawatts has to move from, this is essentially 11 extra petawatts here that have to go somewhere. They can't get out. So 6 petawatts goes out to the north and 5 petawatts goes out to the south. This is for December to February, and it's not that important. This right here shows that the radiative model is wrong and that heat transport runs the climate. This is another nail in the coffin of the atmospheric CO2 nonsense theory that doesn't have anything to do with reality. You got to love how confident I am. That's because I've been looking at this stuff for so long. So any statements about the Earth's energy budget or the energy balance are all averages, like over a whole year. And that doesn't even reflect the real world, because you can the sun can drive energy down into the oceans. It can be stored for thousands of years and come out, millennia later. But I want to correct something from last week that I screwed up, and I owe you an apology. I forgot I also have some announcements I have to remember. All right. That's fine. So I want to correct something right here. So last week, and I've said this before, there's a difference between January and July of 7% less incoming energy. Now, this makes sense because there's 3 million miles. There is 7% less incoming energy. But I've also said that paradoxically, the Earth is 2.2 degrees warmer in July because of the land. You remember that argument? But it was wrong. I was wrong, because of what I want to explain is that it's the same amount of energy coming in, but it just measures differently on the surface. When you measure thermometers or even through satellite, you're measuring over the land. You're not measuring energy going into the ocean. So this 2.2 degrees is really an accounting trick. The Earth has received the same amount of energy in the land and the oceans. Well, the Earth is receiving just 7% less. And what's going up is surface temperature, not the whole planet. The planet really technically should be a little cooler at that time, right? Because it's 7% less. And so it should be some percentage less warm. And that is what's happening, but you get more exposure to the land. And so you get more surface temperature increase. Okay. This is a minor thing, but I said last year, oh boy, there's this big difference between January and July. And if you add 1 degree to that, the whole Earth gets quite a bit hotter. That's not really true, because this 2.2 degrees is not real. It's just a surface temperature change. And on a surface basis, if the Earth were 1 degree warmer, which can't really happen, a lot of that would go into the oceans. So that's what you have to take into account. And it would be a mild increase. All right. So the Earth is always at an imbalance, not in balance. And this is the NASA traditional diagram for the energy budget, showing that this is as much goes in as much goes out as comes in. And that's a lie. And they know it's a lie. It just, if they showed you that there was some heat transport thing, it would be more complicated. People, journalists at the Guardian wouldn't be able to understand it, and it wrecks their agenda. So they say this is the truth, but it isn't. It's kind of never the truth. So I'm going to try to build an incoming heat diagram that is more truthful, less wrong. We'll start with 100% of incoming. Is there a question?
Yeah, that's quite interesting with the temperature difference between winter and summer in the way that you're showing it. It's sort of like, yes, we know that because it's always colder in winter and it's warmer in summer. So we experience that. That makes sense. And all of a sudden, you're just going, so how are they determining their temperature change of the Earth anyway, when we're seeing these fluctuations? At what point are they measuring it? And the other thing as well is about the incoming, outcoming. I mean, every time there's an energy transfer, you know that it's never 100% from one thing to the other. It's always going to be from one thing to a dominant and then some other things. So you have that lost energy aspect. So certainly radiant energy in and radiant energy out won't be equal.
They have to be equal on a space basis. At the edge of it has to be 100% in and exactly the same amount out at the out to space, because it's conservation of energy. There's no friction in nature at the atomic level, at the level of photons.
But if some of those photons are getting absorbed by, say, water molecules or and so on, then and they're changing into either the latent energy or the chemical energy, then they won't be there straight away to release. So the energy is still there, but it's just in a different form. It's not in light form.
Yes, and we can measure photons coming out the top of the atmosphere, and it generally is, over the course of a year, as much energy coming out as going in. If there were a difference, if there were a small difference over many years, we'd go into an ice age, right? We'd have ice sheets. Right. We'd have ice sheets building up, and that does happen. But just year to year, it's pretty much zero. It's pretty much equal. And there are times when we're going into, the Milankovitch, when we're going more toward eccentricity, less eccentricity, it's getting colder. And so every year it gets a tiny bit, like the energy is trapped in the ice, and then it's going to come out later when it melts. I think that's wrong, by the way. I think the energy leaves as it makes ice. So we have a net loss of energy as the Earth cools. And then later as it warms, we get energy trapping as it melts. So you can think of it this way. Actually, think of it this way. Most of the water in the Arctic Ocean is stored energy from in between ice ages. Much of the water in the oceans, 130 meters of ocean water worldwide is stored energy that will come out when we next have a big freeze, a big ice age. Because that's what happened. That's what got released 15,000 years ago. 130 meters of sea level came out of the ice. So whenever you turn ice into water, you're storing energy. So we're storing energy in between the glaciations. Think of it that way. And here in July, the satellites actually do measure warmer surface, but they're not measuring the heat in the oceans. So we're driving heat into the oceans here, but we're measuring a warmer Earth. Now, keep in mind that the Australians don't measure a warmer Earth in summer. Can you mute, Siobhan, or somebody?
Oh, sorry.
The Australians don't measure a warmer summer at all, but the satellites can measure on the land a warmer Earth in July. But it's an accounting trick because the rest of it's going into the oceans. Okay. All right, let's go here. Now, this is the interesting thing that I've spent a lot of time learning and communicating with Will Happer and Javier over the last few weeks. We take 100% of the incoming sunlight and 29% is reflected back. That's called the albedo, right? It's just reflected straight back. It's just shiny stuff or white stuff, white clouds, ice, shiny parts of the water, shiny white stones, whatever, reflects back 29%. And then stratospheric ozone, I thought, absorbed a large amount of incoming energy, and I was wrong. This is incoming. This is high energy photons. Stratospheric ozone absorbs about 3% of that at all times. And the atmosphere itself absorbs 20%. Now, how's that possible? You have to say, well, because water vapor really absorbs energy, but not at these wavelengths. It doesn't that much. And that's what we're going to look at. We're going to try to break this down. Okay. And it's really interesting. It's in basically two parts. The first part is the particulates. If this incoming energy hits the tiny seed, that grain of something that nucleated a droplet, then if it hits that grain, then it can warm up the droplet. Otherwise, when it hits all the particulates in the air, there's a ton of dust. There's particulates that we put up. There's particulates from mountains blowing off the top of mountains all the time. So there's actually a lot of material in the air that absorbs incoming sunlight. And there's also water, and this is something we haven't understood yet. So we're going to come back to this diagram, our favorite absorption diagram, and we're going to look at a part of it that we haven't seen before. This is incoming. All of this on this left side is incoming high energy solar radiation, high energy photons. Okay. First thing to notice is that over here in the ultraviolet, it's all blocked by oxygen and ozone. Oxygen, when it gets these energy, turns into ozone. So it's just blocked. Thank goodness, this is what creates life habitable for mammals. Without this, probably we'd all be, I don't know, bacteria, or I'm not sure, little tiny shell-making creatures and floating in the ocean. I don't know. This gives, there's also some Rayleigh scattering, which is just the scattering that turns the sky blue, that I don't really understand that much about. But if you just look at it, it's opaque here. So this means essentially 0% of these super high UVA, I think it is, just don't get down into the troposphere where we are. It stays trapped up. Well, it just goes to warm up the ozone. That's why the ozone layer is hot. Now here in the visible spectrum, we have a little bit overall, and that just comes from the scattering only in the visible spectrum. That's why we look up and see the sky blue, because you can't see anything over here. But then some stuff we overlooked last time, because we were just looking outgoing. Remember, this is the atmospheric window. This is all going out. Over here, coming in, outside of the visible wavelength, in the infrared, but still high energy incoming light category, we have a bunch of water vapor peaks at different wavelengths, and they really absorb a lot of energy from incoming photons. So we say that the atmosphere is transparent to photons. Photons just come right through. That's not true. Photons in these wavelengths get trapped by any water atoms, water molecules, water vapor, droplets, any water in the air is going to trap very seriously, almost completely here in this wavelength. And in this wavelength, a lot. In this wavelength, quite a bit. And these are wide. And also keep in mind that this is a lot of area here where a lot of photons are coming in. Plenty of photons coming in. Yes, there's more photons over here. This is kind of like volume. Does somebody have a microphone on? Maybe Paul? No problem. So that this area is significant, and this is quite a lot of incoming energy, and remarkably much of that energy, and you can see how much, you know, what about this is total absorption, oh, maybe half or so gets absorbed by the atmosphere itself, by water in the atmosphere. And then over here, this is interesting. Water just happens to have this characteristic that at these wavelengths, it just absorbs all the energy. The difference is, though, that there's hardly any here. There's hardly any photons here. So this doesn't really matter. This is maybe helpful on some other planet, but here it doesn't do a thing. Okay. But here we're really absorbing a lot of photons, and that's what leads us to this 20% of absorption before it even gets down to the surface. So 23% goes into the atmosphere. Contrary to what NASA will tell you, only 17% actually hits the surface. And this is because the ratio of land to water is right here. To the oceans, 31% goes into the oceans. We've already scrubbed out anything that hits the ocean surface and bounces out as a reflection. So 31% actually is absorbed by the oceans. And then, as we'll discuss later, some of this does the evaporation trick and starts moving up in the air column, and much of it goes down into the water and gets stored or moved as heated water. That's where we're going to spend a lot of the time on, because that's the meridional gradient that transports heat poleward. So 31% is going into the ocean. So look, it's like almost 2 times as much, because that's the ratio of land to water as the surface. So this is where the action is in understanding our climate. Does that make sense? And this adds up to 100%, so that somehow, somewhere, it's got to come out. And most of this surface is just going to come out because the surface can't hold or store heat. It's just coming out. It's coming out in real time through the processes that we have discussed. But much of this is heating the water, and that's where we're going in the next few days. Now, there's one more temperature gradient, and that's going down into the water. There's a temperature gradient. That's called the thermocline. It's different at all different parts of the earth and depending on a lot of things, different latitudes. It depends a lot on currents, right? But the thermocline looks something like this, where we have the mixed layer. The sunlight penetrates to about 200 meters. Almost all of it is within 200 meters. And much of that, it's mostly heating the water. It's photons hitting the water or hitting things in the water, and there's plenty of molecules in the water to hit, and warms them. And then much of that heat can get mixed into the mixed layer. And the mixed layer actually differs according to latitude, but let's say it's about 500 meters, the mixed layer. And this is where you get a lot of mixing. It's chaotic, and much of the heat can make its way down. And then heat can be taken down to the depths by the halocline, by the salt water gradients. And saltwater gradients are very different shapes at all times. It's always changing. There's salt currents, saltwater currents, saltier, less saltier. So this is just a random representation, but the salt water is heavier, and it will fall, and it will carry heat down. So you can get tremendous amount of warm water going down into the oceans, and that heat can stay for hundreds, thousands of years. And an interesting thing is, we don't really know how much heat is in the oceans. We believe the average temperature of the entire ocean is between 4 and 8 degrees Celsius. We just don't have enough gear in the water to measure it much better than that. From what I've read, let's say it's an average of between 4 and 5 degrees. It's probably on the cold side of that. The Earth's oceans contain far more heat than Venus's atmosphere just because they're so large. So it's only 5 degrees, but it's much more heat than you find. Remember, it's mass times speed of molecules than you find on Venus's atmosphere, which is hot enough to melt lead, the surface. So here's a question for the science people. What's the coldest, where is the coldest point in the ocean? Where is ocean water the coldest it can possibly be? Anybody?
No.
Marianas Trench.
You'd think it'd be at the bottom, but if you notice at the bottom, I don't have it here, but this is under this. I think this is 5 degrees. Oh, this is 4 degrees right here. You can see this is 4 degrees. So here it's about 3 degrees, and that is as cold as it gets at the bottom of the ocean anywhere. And this is only 4,500 meters, but the bottom of the ocean doesn't get colder than about 2.5 degrees centigrade ever at the bottom. Why?
Temperature of the core of the Earth.
No, it's a good guess though. It's freaking cold down there, unless there's a heat vent, you know, it's brutally cold. Any ideas? What would happen if water would get colder and got down to 1 degree centigrade? What would happen?
It would start to freeze.
It would start to get ice crystals.
So is there just too much energy in the system to allow that to happen? Too much
Oh
movement?
no, what do we know about ice crystals?
Well, they're less dense than the liquid, so they'll float.
They expand. So as soon as you get an ice crystal, it's going to start to go up. So you have a negative feedback here that won't let the water freeze. By definition, it can't freeze because as soon as it gets close enough, it starts to go up. So the coldest water in the oceans is just under the ice. Wherever there's ice floating on top, just under the ice, it's very close to 0 degrees. And that's the coldest you can get in the oceans. Make sense? It's interesting.
Mhm.
That's just a little earth science factoid.
Can I ask
So
a
all of these-
question?
Yeah.
Yeah, okay, I'm still stuck with what Siobhan was saying, right? Because we've just seen all the stuff that stops the heat getting to the earth, i.e. CO2, water vapor, ozone, and so on. So there's going to be an awful lot. I mean, there are areas you say where the photons just go straight through, and because photons are just very small, but there will be a lot of friction on the well. There must be some loss of energy on the way up.
No.
And also because people, I mean, just to put the other side of the story, you know, there's a huge number of particulates and whatever going off up into space from all the stuff we do, like car tires and so on.
No, they don't get to space. They don't get anywhere near space.
But they still stop stuff going out.
Oh, there's tons of it in this troposphere. There's
Yeah.
lots. Yeah, it just warms up. It's just there's conservation of energy. It's all happening at the atomic level. There's no friction. So if a photon is stopped by something, it transfers 100% of its energy into whatever thing that it's now vibrating.
Oh.
All the energy, 100% of energy is conserved.
Okay, at that point of contact in between, but I don't know any science, all right? I'm guessing.
Yeah.
So but presumably at that point, when the photon hits water vapor, does the point I think Siobhan was taking is that not all of it will go into that piece of water vapor. There will be go some other place.
It doesn't matter. It has to go somewhere because
It has to go somewhere. Yeah.
at the level of atoms, everything is a perpetual motion machine.
Okay. Yeah.
Everything. There's no friction at the level of atoms. They go forever. And you know, the electrons spin forever, right? Around the nucleus. There's no slowing down. There's no old atoms that are slowing down. Everything's just essentially going the speed of light one way or another.
Hey, it's crazy, man.
It's crazy. It is crazy. Our brains aren't designed for this, but there's 100% preservation of conservation of energy.
Okay, that gets me a bit further. Thanks.
So all of this energy coming in must come out, or the Earth is getting warmer and going toward hothouse Earth, or more comes out and we're going toward ice ball Earth. These are very slow processes, like, you know, 1 million years. So year to year, it's very, very similar. It's not exact because we might be getting colder or warmer, but it's like riding a bicycle. You know, are you ever in balance on a bicycle? You're never in balance. You're always falling on a bicycle, right? And then catching yourself. It's like that. Does that help? It's never in balance. Now that all leads to the distribution of energy along with the shapes of the continents gives us the meridional temperature gradient we have today. And that's this thick blue line right here. This is the latitudinal temperature gradient. It's also called the meridional temperature gradient. It's the tracks on which the heat pump runs. We're going to learn more about the heat pump. So at the highest level, the continents and other factors determine the shape of this line. And the shape of this line determines our climate more than anything else does. Okay, that's the second one. And these are the three, and actually four, because of the water temperature gradients that move heat to space. All right. Now we have the ITCZ, and I'm just conscious of time because we're getting close, but I want to run through this one and then we'll see if we have time for the next one. The ITC, who knows what the ITCZ is, or ITCZ, I guess. What does it stand for?
The International Time. I don't know.
Intertropical Convergence Zone, right? We knew that. The ITCZ is the Intertropical Convergence Zone. It's the Earth's climatic equator. It isn't two lines. This is where it is in July. This is where it is in January. It's just a single line that moves north and south during the year to follow the sun. In July, it's farther north. In January, it's more south. And this line defines the tropics and determines the weather patterns in each hemisphere. If you've heard of the doldrums are always on this line where there's no wind because it separates the two hemispheres. It separates the drainage or the air cells come to converge here, so there's nothing going on. It doesn't drive climate. The ITCZ is not a driver. It's an artifact. It's a record of the temperature gradients and pressure systems that move energy along various paths from the tropics to the poles. It's more of a record of the division of labor between the two hemispheres. Right at the ITCZ, wherever it is at any one time, we have no wind. It has its shape because of the way the currents move in the air, but also because of the way the air currents over the mountains and the basins on the continents. And look over here, it really moves it up here near the Himalayas. It really pushes the flow of air around according to both what's going on in the water and what's going on over land. Okay, and it can move the whole thing kind of periodically every 6 months does this, but the whole thing over decades can move more south or more north. And I'm going to show you that right now. So here is the equatorial flow traveling west. Why is the equator flow always west? Because the Earth is always turning east, right? So that's the Coriolis effect, right? It always is going, the water is always going west at the equator all around the world because the Earth is turning the other way. And when the ITCZ is more north, as it was during the medieval warm period, and it is today, the eastern point of South America sends most of the incoming warm water northward into the Gulf Stream. This is hot air coming out of Africa, and going into the ocean. So this is warm ocean and air currents both coming this way. And that Gulf Stream takes that heat to the North Pole, and some of that heat goes down to warm up Cape Town and the southern hemisphere. This is the period we're in now, but when the ITCZ is south, less water goes north. So the Gulf Stream has less energy, and more energy heads to Antarctica, where most of it can escape to space. And so this is a colder period overall. Something similar happens in the Pacific with the El Nino current. So you see that the ITCZ determines the amount of energy going north and south. Now, the ITCZ itself moves north and south, and we know this from drilling a lot of cores and looking at a lot of sediments. It actually comes from titanium, what are they called? Titanium isotopes. And this is a proxy estimate then of the north-south movement of the ITCZ. Notice that this is not per year at all. This is 1,000 years. So each of one of these measurements is probably around 10 or 20 years. And so over the course of 150 years or so, it can move a lot. But in the course of 1 year, it doesn't move much. Okay, and so it was much warmer here in the medieval warm period. Then it has an interesting warm period here, and then it really fell during the Little Ice Age. And so this kind of reminds you of what? Sunspots, doesn't it? This is the Maunder minimum of sunspots. And sunspots determine a lot of these variations on this time scale. And so this is kind of a record of the incoming sunlight as produced by waves of sunspot, variance over time. Okay. And that moves the ITCZ, which changes the currents. I'm trying to get now more toward the currents rather than the temperature. You know, we saw that we had the Maunder minimum with the temperature was lower during the Little Ice Age. Yes, but also the currents have changed during the Little Ice Age, more like this during the Little Ice Age. So there's less energy available to heat. This is how you get all those ice fairs on the Thames, because you have less warm water coming through the currents. All right?
Mm-hmm.
All right. And so that just kind of manifests itself in more or less water coming up into the North Pole or to the poles in general. So as the ITCZ shifted northward in 1820 or so and has been shifting northward since, it started sending more water to the Gulf Stream, more filling the Arctic with channels of deep warm water. And this is probably what ended the ice fairs on the Thames and is responsible for the warming we've seen over 200 years. Nothing to do with CO2, has to do with currents. All right. I think that this is pretty well correlated with sunspots. And I think this is, again, the ITCZ is not a driver. It's a record of how temperature fluctuations influence air and water currents. It's an artifact. It's not a driver. All right. Now, I'd like to do the jet streams. I've got the jet streams and the polar vortex. That will take about 20 minutes. Can most people stay for that so that it's recorded? Is that all right with most people? All right. I want to do 2 short units, and this is really interesting. And this is, again, just kind of an introduction, and we're going to go more into it later, as we're just going to use all these bricks we're laying down. So The Earth has 3 primary air circulation zones, which you've probably studied already because I put up a video on it. The Hadley cell, the Ferrel cell, and that's also called the mid-latitude cell, and the polar cells. Okay.
Oh.
We're going to look a lot more at these next time, but I just want to give and orbital mechanics is wrong. But the ITCZ is the dividing line for the 2 Hadley cells. So that moves up and down during the year, and so do the Hadley cells. Okay? Not on the equator. It's on the climatic equator. Before we get to the big cells, I want to explain the jet streams. They run from west to east in the entire planet. And there are 2 big ones up here and 2 big ones down in the south. The subtropical jet and the polar jet. Heat rises from the equator, creating a zone of low pressure down here. This is getting sucked out, so there's low pressure down here. Then the Hadley cell brings air away from the equator, drops its water in the tropical storm, so this is tropical weather, and by the time it gets to 30 degrees, it's very dry. And it's about a mile up. So this creates the subtropical jet. Now, down on the surface, that brings, as it falls, that brings high pressure. And these are the deserts. This is very dry air, high pressure deserts all around the world. Low pressure, moist air, tropics. Okay. Creating the deserts is the Hadley cell creates the deserts. And the Ferrel cell then can pick up some of this air and bring it north, but really the Ferrel cell is its own cell. And so it's recirculating here. So much of the air coming down into the deserts from here goes back. So this really just circulates. And this one really just circulates. And we'll see later that this one just circulates as well. So this is just recirculated air. So right at the boundary, we have the polar jet. We have the subtropical jet. And I want to help understand what makes that. I want to see. This is because these jets drive our weather systems, right? The jets occur where the 2 cells converge and the temperature gradients create pressure. So there's pressure there. That creates a narrow, dense mass of air that moves eastward. Why? They all go eastward because of the Coriolis effect. It's a mile up and the Earth is turning underneath it. And because the Earth is turning, we think that we're stationary. Actually, what's happening is the air is stationary and we're going underneath it. So the air moves east. And this might take a little minute or rewatching this to understand this, but the Earth is going underneath. And so the air, that driving air, it's like a shear layer driving air eastward because it's a dense mass of air. So what creates the jet is dense air getting left behind by the rotation of the Earth. And these jets are near the top of the troposphere, although this one is higher, subtropical jet is higher than the polar jet. And that gives it more energy because there's more Coriolis and more wind speed. So the subtropical jet is faster than the polar jet. And because of air density and the Coriolis effect being stronger near the equator, this one is almost always faster. So I said that. So now those are the jets, and that's just a quick overview of those cells that we're going to get more into. Now we're going to go to the polar vortex to wrap this up. The polar vortex is above the jets. The jets are down below the tropopause. They're about a mile and a half off the ground. And the polar vortex is in the stratosphere above the weather, where the jets fly. It's going to be 30,000 feet or greater. The polar vortex is a large, swirling mass of cold air that circulates around the Earth's poles almost all year round. It's almost always in the stratosphere and can extend down into the troposphere when it's weak, especially during the winter months when it weakens. So this polar vortex creates a low pressure funnel above the poles that sucks heat out and lets heat escape to space. This is actually part of the whole heat pump, that where once the heat gets to the poles, the vortex forms like a highway for it to get out through low pressure and upward currents going to space. And then as soon as that energy can get to transfer into photons, then it just radiates away. The polar vortex is strongest in the winter, especially in December, when the temperature difference between the polar regions and the mid latitudes is greatest. And the winds generally go counterclockwise around the poles in the northern hemisphere and clockwise in the summer in the southern hemisphere. That's obvious. But occasionally, the polar vortex can be disrupted by events that are called sudden stratospheric warming. I should write that here, but it's on another slide. During these sudden stratospheric warming events, SSW events, the polar vortex weakens and the overall pattern can become distorted or even break into two separate vortices. And here's an example of two separate vortices. Now, in some cases, warm air from down low, and this is called the Rossby waves, just for the name of it. These are Rossby waves. This follows the jet, okay, because it's distorted. This comes down low enough to distort the jets, or the polar jet anyway. And so the polar vortex's winds weaken as a result of heat moving into them and sort of knocking the wind down. So it's not a great way to put it, but these are episodes. They are part of the heat transport mechanism. You can think of it like this. There's a buildup of warm air in the temperate region, and when it gets enough warm air, it can punch into the Arctic, and that will disrupt the vortex. And these disruptions can influence weather patterns in regions far beyond the polar areas, leading to very cold outbreaks or unusual warm. So I want to show you one here from 2015. This is an unusual one. They call it polar vortex shutting down. When the polar vortex shuts down, it means that the vortex weakens and the winds, which are usually very strong and fast, slow down. And they can even reverse direction. So here I want you to see, this is temperature and this is wind speed, okay? See how it's the temperature, a mass of warm air builds up and shoots north because of something. And when it does, that slows down the speed of the wind. And then when that air dissipates and it's no longer coming, then this speed goes back up. This is wind speed. But then when a large mass of air comes north, not only does it slow down the wind, here's zero, but in this case, it reverses the wind and actually went pretty strongly in the other direction. Reversed the wind to now going clockwise or to the west, from the east to the west, for a couple of days, for a couple of weeks here. This is a very unusual event. This is 2 weeks of the polar vortex going in the wrong direction. It happens, but it's pretty rare. Okay, and it's driven by the heat spike. So it's not driven, the wind change is a reaction to the temperature gradient change. That makes sense. So here's another way to look at one of them. This is from 2021. You see how the warm wind, here's temperature. This is wind speed. This is temperature. As temperatures rise on January 5th, they peaked, and that dropped the wind speed to zero. See that? When the temperature peaks, the wind speed goes to zero. There's still it's quite hot and it's building up enough to reverse the wind speed. So here we have it's going slightly, not very quickly, but it's going in the wrong direction. It's going westward for 4 days, 4 or 5 days. As the temperature comes down, that wind speed stops again, and then goes back the normal way for a couple days, and then the heat comes back, and then it drops it down to 0 again, and then goes the wrong way, goes back to the west for another, I don't know what it was, 10 days or something. And then as the heat comes down and is dissipated, then the vortex resumes. So this is called sudden stratospheric warming. It always affects the vortex. And in 2020, oh, this is 2020 and 2021. In 2021, it happened twice. There were 2 times when the vortex went west rather than east. See that? And when that happens, when the warm air goes north, this is again through the Rossby waves. You know, there's a wave of pressure pushing hot air north. That creates what we call the hot north, cold south arrangement, which I think you also have in Europe, but someone asked me about it the other day, and I said, I really don't know. I can't give you any, but you could probably look it up, and there's probably something similar. In the United States, it almost always happens in January, February, and it can be warmer in Alaska than in Florida. Now, Florida is pretty warm, but it can have colder temperatures here in this panhandle of Florida than you do have in Fairbanks, Alaska. And that happens once in a while. I'll explain that in how often it happens. This is the normal flow being disrupted by warm air, and so it's chaotic. Anything can happen at that point. And this is called, unfortunately, polar vortex breakdown. It's a technical term. Polar vortex breaks down because the usual laminar flow around is disrupted by chaotic mixing. Now, unfortunately, lay people, like all my Facebook friends, think this is caused by humans burning fossil fuels, and they say, oh, it's breakdown, it's destroying the weather system, the polar vortex has been destroyed. They don't know what the polar vortex is, but they're sure that humans have killed it and wrecked the climate system. And there's only one problem. It's been happening as long as we've been measuring it. Here we've measured it a bit back in the 1850s. It happens. It's a normal feature of meridional heat transport. It's been happening since we've been measuring temperatures, and it tends to happen about 6 times per decade. It's not regular, it's irregular. About 6 times a decade, the vortex breaks down. So we should expect to see a sudden stratospheric warming event every 2 years. It's always January, February. Some years have 2. You can see some years are really very active here. And we've even seen one year has 3 such events in a single year. I forget which year, but one year has been recorded with 3 events where the wind went to 0 or even reversed. And in fact, we've had 2 already this winter in 2024. Yes. And this is how they portray it in the media. It's a field day for journalists at The Guardian who don't understand anything about climate mechanics. So when you hear the vortex is collapsing, and obviously it's the end of days and humans are doing it, it's not normal. It's got to be, you know, it's got to be the destruction of nature by humans. Ask them, when you hear that, ask them, how often does this happen? The answer is about 6 times every decade since we've been able to measure the Arctic, and certainly for hundreds of thousands, if not millions before. So now that is my presentation for today. I've got one bonus, but I don't want to push everybody too hard. I've just kind of laid that foundation down. Do we have any questions or comments about that?
think I'll need to revisit some of the graphs, look at them a bit.
I mean, you're never going to remember any, you know, if you can remember 5% of this, you're doing great. Right. I'm just trying to influence your mental models, right? About, okay, it's really not about temperature. It's really about pressure systems and currents. That's where the action is. Comments, questions? Imani, yeah.
So I saw a video on something about sunspots are coming at an unusual amount of time, which is a precursor for the magnetic charge of the, or that protects the earth actually adjusting, and that these blasts from the sun have been very infrequent over a long period of time, but that's something like we've had 5 of these bursts from the sun adjusting the magnetic kind of bubble around the earth, and that this is a presage of the magnetic poles changing. And so I was wondering earlier in your lecture about, you were saying sunspots, right? Sunspots has this effect. Is there a dovetail between this idea of, because meaning are sunspots what people are talking about is having this magnetic effect? Because they were talking about, look, we're seeing aurora this year much farther south than is typical. And so I didn't understand if what you were talking about had an intersection between magnetism of the earth in relation to activity of the sun, and then we were talking about it in relation to temperature.
So anybody is welcome to research this. My understanding of magnetism is that the Earth's magnetic pole flips whenever it wants. It's absolutely not regular. It's random. And nobody knows. Maybe someday we'll be able to predict it, or we'll have a mechanism for it. But at the moment, my understanding is we have no idea. And it could flip tomorrow. Or it could flip in 10,000 years.
Magnetic north is it's on our sea charts, and you have to adjust your compass, and it's measured on the sea charts, so it does change, and it does,
it's always moving. You can see maps of the trace of magnetic north where it's wandering, right?
But then sorry,
it can flip. It flips.
Yeah.
I don't know, on average, I'm not sure how many, I wouldn't want to say a number because I'm not sure. I think it's about 20,000 years, but I'm not sure. But it's very irregular. The average doesn't really help because it's super irregular. Sometimes they're close together, and sometimes they're many, I don't know how long in between.
So when you're talking about sunspots in relation to the information that we're reviewing together, it doesn't intersect with this idea of magnetism and the effect that has on the earth.
Not that I know, but it has a lot to do with temperature. Sunspots and temperature have a lot to do with each other. And these sunspots, they come in groups every 11 years. We're in number 25 right now. Sunspot cycle 25. We're at the peak of 25 right now. And then they go in these little groups that get more and then less and less. And so every 65-ish years, we get a full cycle of them. And that's related to the 65-year cycle that we're going to talk about. And then some of those cycles are much more, and some of those are much less. And we know the Maunder minimum that caused the little ice age was very sparse. And we've seen periods of hundreds of years with practically no sunspots. And then it's very cold. So there's people who really study this, and I don't. So if anybody wants to get more serious about it, there's Zarkova and plenty of literature on sunspots. And it's all very much part of the system, but it's not the whole story. So I don't know about magnetic. Now I have a bonus if anybody's interested. Anybody want to stick around for a bonus? Because I'll record it. All right, let's go. All right, this is about precession. This is about sorry. Let me just get it. Let me get the right deck here. It's going to be wrong. Oh, there we go. Okay, good. This is about precession. This is fun but hard, so I need you to have your green juice or your super kava or whatever your product is that gets your brains going. It's only one slide.
Sleep.
We mentioned this a couple of weeks ago. We mentioned that this is the last 20,000 years. And there's a mistake in the in the x-axis here. It should all just be thousands of years, 10,000, 11, 12,000, and 20,000. And this is the last ice age. Here, the peak of the last ice age is actually somewhere in here, but this is the coldest temperatures. This black is temperature. And I want you to see 4 different parts of this chart. We've got a very consistent, cold, flat, cold period. We have a very volatile coming out of the cold period. It's like hard to know if you're really coming out or going back in. And then it peaks up here at about 10,000 years. And this is the beginning of the Holocene. It's very flat for 5,000 years. It's like 5,000 year increments, 5,000 years flat, 5,000 years crazy, 5,000 years flat, 5,000 more volatile. Never know where it's going to go, but we've seen that this has really crushed a lot of civilizations when it goes down. It's the end of the Bronze Age in here. And this is the Roman period building up, and this is the end. And this is, the medievals and all that stuff. We've been through that. But it's more volatile here for the last 4,000 or 5,000 years than it was here. It was very remarkably stable. Now, we also know from the period of time when we looked at this before, this doesn't repeat. You're not going to find this, 21,000 years ago or 46,000 years ago or 26,000 or 41. You're not going to find it because a lot of things are going on in the orbital world of the Jupiter and Saturn and, where everything is and what's pulling on what and what the shape of the dance of all these, massive bodies. And so it doesn't repeat, but I see something super interesting here. Obliquity is doing its thing, which is, we're peaking at obliquity, which means the chance for the ice sheets to be beaten back by the sun. Remember, I've drilled it in that obliquity has to get higher to have a chance for an interglacial, and we have one, thank goodness. It was no fun back here. This is where you need to kill a deer and get its skin on yourself to survive, and then you end up being Uli the Iceman, and it's frozen in the Alps or something. But here, we had a chance, and it did. This window opened, and it worked, and we have this calm or period of less volatility. And so I want to map that to precession. And this is the hard part. So this is the tricky lesson here that I'm going to explain probably a couple of times with my usual sun and earth. I've noticed also that the proportions are not right, but just for, just humor me. As I've tried to show before, we're at an angle, and the angle does change. I mean, look at obliquity, it's changing. Okay, all right, it's changing. I'm not going to show the change of the angle. I'm just going to assume that it's the same angle for now. And over 46,000 years, that angle changes. But over 21,000 years, what happens? What happens is, the signs of the zodiac, the Polaris, the North Star changes, and we wobble, one wobble in 21,000 years, right? And that's one 21,000 year cycle right here. This is one full wobble. So wherever we were today, that's how we were when it was brutally cold back here. And no surprise, it's cold now. But I'm going to try to show you how the precession can cause this or play a big role. And it's tricky. So first, I'm going to start with the extremes. The two extremes are what we have today. And what we have today, we're farthest away when it's July. Right now, the Earth is farthest away in July. And that is means that the southern hemisphere gets the hottest summers and the coldest winters. So for the Australians, it's extreme. And for us here in the north, it's mild, right? And then in 21,000 years, 10,500 years, we'll call it in 10,000 years, that'll be the opposite. It will have wobbled around like this, so that in 10,000 years, we will have the hottest for us, and our summer will be in January, and our winter will be in July, and it'll be very extreme cold for us in the north. Everybody see that? So what's tricky to show is that these two extremes happen along the axis of eccentricity. So eccentricity is an ellipse and it has an axis. And it's at these two extremes during our time right now and during our time 10,000 years from now. And in between, we're making this rotation of the axis, and it's not as clean. So we don't have the same kind of, sort of think of it, this way now. We don't have the same kind of extreme exposure to the land that we have in today's world. Today we have mild north, extreme south. Okay, but halfway around, it's kind of in the middle of both. I'm probably shouting a little too much. It's kind of in the middle of both. So I'm gonna propose that we can visualize that this way. Okay, this is the extreme right now, which is our mild. And this is going to represent the extreme the other way, where 10,000 years from now, it's our hot or it's our extremes. Make sense?
Oh.
And here is in the middle. Here is precession in the middle. It's going like this. Every 21,000 years, I'm representing the wobble in this way, only because of the exposure to the northern hemisphere. So I'm recreating it in a different way. Does that make sense? So here it's extreme, here it's extreme, here it's extreme, every 10,000 years, right? What happens in the middle? Mild. And look, every 5,000 years, mild, extreme, mild, more extreme, more volatility. You see that? So this is my hypothesis that the orbital mechanics just happen to be set up right now, just because they are, to show us that this extreme temperature variation, and we're actually going to look at this in another unit. This comes from what are called the Dansgaard-Oeschger events and the Heinrich events. Heinrich events make cold, Dansgaard events, Oeschger events go warm. We'll discuss it. Don't worry about it. But they're set up by the extremeness of the temperature swings from summer to winter in each hemisphere. And the same thing here. And it wouldn't surprise really any Earth scientist, if you really look at this, to find that we'd have some fairly extreme temperature excursions as a result of the setup right now. And that this ridiculously mild, this is unprecedented, this is just insanely mild. You can go back like 3 million years, you're not going to see another 5,000 years like this. But I think it was set up by precession. And this was set up by precession. And probably, and I haven't done the research, and I challenge anybody who wants to, you can go back and look at the fine grain of this, every, like, you got a temperature measurement here every, say, 500 years or 200 years or something. If you look that fine at it, 1 million, 2 million, 3 million, 4 million, you're probably going to find somewhere else where things line up and you get something similar. That's my hypothesis. Somewhere back there where things are similar enough that you're going to get this 5, 5, 5, and 5 regime again. And that just is kind of an insight I had about precession. So I thought I would bore your pants off with it. If that's okay.
Very good.
Another little science factoid that may or may not be true, because, you know, it's just all part of a much bigger, more complex machine that we don't understand. And so are the magnetics. Anybody who wants to research the magnetics, please come tell us about them, because I don't know about this magnetic flipping. But, you know, when you say, oh, we have unprecedented northern lights, unprecedented what? 100 years, 200 years? You know, really? Doesn't mean much. Doesn't mean much. The Earth's been around a long time. We don't know what unprecedented really means. All right. Comments or anything?
Well,
yes, Dan.
So if we look at that last graph again, and you don't need to put it up, but I think we all saw it. If we can extrapolate, it looks like it's going to get really cold.
We will discuss that. And Javier has a whole chapter on this, and we're going to talk. Remember that we're in a 11-year cycle that's at its minimum, and it's about to start going back up and getting more and getting bigger. At the same time, we've got this stuff going on. You know, where are we in all of our cycles? You know, so it depends. It's interesting when you say that, because from it depends on the time frame you want to talk about, right?
Right. Well, I'd say like the next 1,000 years appear to be cooler than the last 1,000 years, based on that. The red line and the green line are both heading down.
It's true, but the sunspots at that scale, the sunspots have a lot to do with it. So my preview and my overall sense is that the next 100 years are going to be very much like the last 100 years. But 1,000 years from now, yeah, we're going to be turning down. Yeah, that's true. I don't think we can get away from that. I think it's, some people say within 500 years, some people say, you know, but at some point, 500 to say 1,500 years, those ice sheets are coming back. But Javier says, and we'll talk about it, that the ice sheets won't be as bad as last time. And I have no idea why. I've only read it twice. I'm going to have to just, you know, make my little presentation about it and try to convince all of us, and hope that you don't notice where I've screwed up. But as far as I know, temperatures are going to be going, you know, I'm pretty sure we won't be around. So
I'm not going to be.
so I don't know who it matters to, but in the next 100 or 200 years, it won't really surprise Javier or me if temperatures go up a bunch. And that'll be another extended period but long before then, the net zero thing will have crashed and burned, and we'll be on nuclear power.
Yep. Yeah, can I say something about that?
Yeah.
Hello? Could I say something?
Yeah, Corin.
Yeah, I think it will crash and burn. I mean, Professor Kelly at Cambridge was saying it'll cost 4.75 trillion quid in the UK to do this net zero. Michaud says there isn't enough copper. Even you get the copper off the sea floor, it's not going to happen.
Right.
The National Grid says it'll cost 104 billion quid to wire up the grid to take intermittent power. So people now have a big incentive to come to a different conclusion. So it may happen.
I don't know when. Like they say, the markets can stay irrational longer than you can stay solvent.
That's quite true.
So I don't know when.
Oh.
Because it's such a huge moneymaker right now.
Well, yes and no, but if you can't do it, I mean, at 4.75 trillion quid, I mean, they've spent all the money already. There isn't any money.
Oh, there's tons of government money. Look, a bunch of lawsuits in a bunch of law schools in the United States not only have climate law classes, they have climate law degrees.
Bless them.
When is that going to peak? It's just getting started because there's so much damn money involved.
Well, I mean, that's what the carbon credit stuff is about. It's because our current financial system is absolutely up the creek. I mean, the money isn't worth anything. The numbers don't mean anything. But the beauty of having carbon credits is that, with life being carbon based and most of our resources being significantly carbon based, it's an energy monitor system. And so if you're a good person, you can have a bit more. And if you're not, then you have a bit less. And so on. So it's
a control
the
mechanism.
Absolutely. It's technocracy, cybernetics, and choosing carbon as the measure is really quite clever, because you really are measuring everything about life and all the movements and the transfers, energy transfers that are going on the planet. So it's very, very clever, but it isn't very good for us. So
you're gonna try to book a flight, and it's gonna say, "Oh, too bad, no flying for you."
Yeah,
you've already used it up.
Yep.
No more. Sorry. Yeah, it's just all nonsense. And the carbon credits that are trading in the carbon markets and all the Apple says that they're 100% renewable. You know that's just all fraud.
Well, the computing power required to do all of this, I mean, the energy required to run the machines to be able to do this must be phenomenal.
Yeah.
And if anybody's actually worked that out, I don't know, but it would be very interesting to see how much energy is being put into the surveillance grid and what the carbon credit of that would be. Because as soon as we cut the electric, it all goes down, doesn't it?
It's all circular reasoning.
Mm-hmm.
Yeah.
But if it controls us, it's very good for them.
But I'll tell you, all these big consulting firms, oh my God, they have thousands of carbon consultants now. It's just a field day. It's just a bonanza for consulting, carbon consulting, carbon finance, carbon accounting, carbon audit. Oh my God, it's great. Well, what's not to like? More regulation. Bring it on. Anybody else?
No.
Okay, well, I hope you enjoyed that. That's just a bit of tidbits of just droppings from whatever comes out. We are heading into the heat pump, so hold on to your hats. Remember, I've got a few announcements now. Number one, there is a Google Doc where you can put what you're up to and interested in, so we can have that forever, so we can just look each other up and say, oh, I know somebody who lives there, or I know somebody who I could visit or call and just, help out, whatever. So that's in the Google Doc. I know a bunch of people have asked for access to it. You'll find the link in the system. Number two, next week on the, whatever it is, May 1st, on Wednesday, May 1st, it's at 5 p.m. UK time. That'll be at noon my time, noon US time. I am recording the heat conversation that I had with Mike at the very beginning, just to have it and have it in the system. And if you can come and be in the audience next week at 5 p.m. UK time, you're welcome. It's no big deal. It's Wednesday next week. And then finally, the system, people have been asking me, the system will be available for you guys in perpetuity. You'll just always have access to that stuff. It's stuff I'm not making public because I want to, build up my class business. And then, I just hope that goodwill spreads and that you help me get other people. When I have another class, I'll let you know and you can help me publicize it.
Okay.
So, whenever you need that's always there.
Very good.
Other questions?
No.
I have one. Sorry, beg your pardon.
Thank you very much. I'm going now. Bye-bye. Thank you.
Thank you.
David, I have a question about nuclear.
Okay.
Can I ask what you just made a comment about that the future is nuclear?
Sure.
Does anyone in your sphere ever talk about the problems with it rather than the solutions that it offers?
Sure. First of all,
do they weigh heavily on people or not?
We've got fission, And fission has what I understand is called a deuterium problem. There's a lot of things that make it really hard. I am a big proponent of small modular nuclear reactors with thorium. Thorium has huge advantages. I've studied thorium a lot. There's a thorium alliance that's trying to get it, less regulated. And so my view of it is that eventually we'll have to overcome a bunch of these problems. But the deuterium problem is for fusion. I'm sorry, not for fission. That thorium is kind of this ideal fuel that can produce its own fuel, and that over time, you can imagine a small nuclear power plant on a tractor, bring it into town, set it up over a week, it's running, turn it on, connect it to the grid, and then in 10 years, it's out of thorium. How much thorium do you need to power a town for 10 years? Not that much. It's like a suitcase, roughly, of thorium. And then at the end of 10 years, they'll just bring it back to the factory and refurbish the whole thing and send replace it with another one.
And then what happens to what's been left behind?
Oh, with thorium, it's not that much. Thorium is fantastic. Thorium essentially just breeds its own fuel. And it also is safe and doesn't take thousands of years to whatever's the waste product is. It's not magic. It's not perfect. But of all the trade-offs, thorium is to me, and I don't spend that much time. I'm open to other.
So is that the key phrase, the trade-off?
Well, you're always going to have trade-offs making energy.
Yeah.
I mean, what if we had half as many people or twice as many people? We'd have a different energy problem. Sure. But I think we will figure it out and scale it. And I think it will be probably fission before fusion, but I also think fusion has tremendous. I think we're going to get fusion at some point, maybe not in 20 years, but I think it will make it commercially viable. Yeah, Dan.
I don't any longer have Netflix, and I don't know what kind of Netflix stuff's available in the UK, but I watched a documentary, and I'm no Bill Gates fan, but this was a Bill Gates thing about nuclear.
Yeah.
And it was really intriguing that the new technologies that they're talking about cannot melt down.
That's right.
That's right. In the same way that the current ones are. So right. I'd recommend that to people who, if they have Netflix, it's probably still out there somewhere.
Let me just, Sam Altman put a bunch of money into a nuclear fusion project, and there's some very good short video on that, and it's called Helion Energy. And so there's great videos on Helion Energy, and there's very interesting. I sort of think the tokamaks won't work or I don't know, but I think the tokamaks are just these huge government projects that are so big that, they're not $10 billion. They run over budget by $10 billion. They're just too huge. So I'm looking for smaller, more modular solutions.
Well, maybe you can get a Mr. Fusion like they had in Back to the Future.
Well, look at Helion. Helion's pretty exciting. There's some wonderful videos on Helion. And there's a bunch of others. There's going to be some good stuff here. But there is, I think, a deuterium problem where if I remember correctly, it's going to be easy to run out of deuterium and you're going to need a lot of it. I don't know. But I just think these problems will be solved. And I think 100 years from now, it'll just be normal. I mean, the poor French, they were just running their country on nuclear power for decades. And then boom, came the net zero stuff, just destroyed their energy infrastructure. Just at the time when Putin invades Ukraine, really bad. I feel bad that the French have, a bunch of crazy greens, and yet they were so sensible before.
Yeah, well, if you control, again, it's controlling of the energy. So the research into nuclear in the Western countries has been significantly downgraded since the 70s. You probably find that there is much more advanced research into the nuclear stuff if you start looking around at the BRICS countries. And stuff
China.
like that. So definitely China and Russia.
China has a lot.
And I bet India is on a catch up as well. So yeah, if you're wanting for up-to-date research, it's probably to those sort of areas that you actually need to really look rather than in the Western science.
Yeah, China is pouring money into thorium.
Mm.
Yeah, so I think small modular reactors, the size that you can put on a truck, or that because that why? Because that democratizes energy. Companies can buy them, cities can buy them. It's not a giant government, billion-dollar thing. That's what's exciting about it. And money.
Is that going to democratize the radiation?
I just don't think it's going to be an issue. I think it'll be contained. I
think?
Yeah. Sure.
Certainly, I haven't looked in detail at it, but it sounds to me that the sort of like the old ideas where we had the uranium, and then you've got this massive waste problem, and we've got to fill it in all the caverns up in the Lake District and all that.
Yeah, that's all.
That kind of stuff is well out of date now, and
right.
certainly from what I'm reading and I'm hearing, is that the radioactive waste issue with nuclear is significantly reduced.
That's right.
And a lot of the energy, as you say, with the thorium, it's recyclable.